There you are.
All right, my name is Tritt, and I did my speech on vertical heat exchanger. Today's agenda is definition of what a vertical heat exchanger is, what it is, how it differs from horizontal heat exchanger if it does at all, and the basic principles. Then a description of the lab I did, and the results in table and graphic form, and a final conclusion. What is a vertical heat exchanger? In chemical engineering, a vertical heat exchanger is a unit op, a basic step in the process which utilizes heat transfer from one medium to another. So essentially, a heat exchanger is a piece of equipment that is specifically designed to help control or change the temperature or phase of different substances in the process. There are two primary classifications of heat exchangers based on flow arrangement. You have parallel or concurrent flow or countercurrent flow. In a concurrent flow, the fluid enters the exchanger from the same end of the exchanger, the same end to the exchanger, and travel in a parallel, similar direction. While in countercurrent flow, fluids enter exchanger from opposite ends and travel in opposite directions, parallel, transferring the heat from one another. The countercurrent design is assumed to be more, not assumed, is believed to be more effective, and usually is more effective, in that it can transfer the most amount of heat from one medium to another due to the average temperature difference is greater than parallel all the way through. There are also several different types of heat exchangers. I don't have enough time to go through all of them, but the basic one we used in the lab was the shell and tube heat exchanger. It is one of the most common ones. The heat exchanger consists of a series of tubes containing the fluid that you're going to transfer heat to or from, which is inside a shell where the second fluid flows through, and it flows over the tubes, causing the conductive heat or convective heat transfer to occur. Difference between horizontal and vertical heat exchangers. Basically, there is no difference between horizontal and vertical heat exchangers. There's very little that changes. Some of the minor changes would be depending on the process and space provided, the orientation one might be forward over the other, depending on how much space you have and whatnot. The phases changes occurring, one might be better than the other. As a vertical one, the gas would be less dense than air, so it might rise, be easier for it to get out of the vessel. And lastly, the horizontal heat exchanger might have a higher or more resistance time than a vertical heat exchanger, and this can be due to the orientation of it also. Basic principles. The main purpose of the heat exchanger is to change heat from one medium to the other in order to change the temperature or phase of a product, like I said before. This transfer is guided by the basic equation of Q equals mCp over T, where m is the mass of the substance that's being heated or cooled. Cp is the heat capacity of the substance at constant pressure, and the delta T is the change in temperature of the substance, where the leaving temperature is subtracted from the beginning temperature. Now for the lab, the objective of the lab was to determine the amount of heat transferred from the system, from steam to liquid water and heat exchanger under varying changes of flows, pressures, and flow arrangements. For the first trial, we used 14 psi for steam and 4 gallons per minute of the liquid water. On the second trial was the same pressure of the steam, but increased the flow of the water to 7 gallons per minute. And the third trial was 8 psi of steam and 7 gallons per minute of water. For the last trial, though, it was done as a countercurrent flow instead of co-current. And the steam pressure was at 14 psi and the liquid was at 7 gallons per minute. This is the results. This is where I averaged them. But, at the first trial, you can see that the first two trials are pretty much similar, based on the conversation of energy, pretty similar to the heat gain and loss. In the third and fourth trial, though, the delta T of the liquid was very high. And for the last trial, the reason is that the water was evaporating. The cold water was evaporating, causing heat of vaporization, increasing the amount of heat gained. The third one, I'm not quite sure. It's the average of 3 runs we did for each trial. And this is the graph. The liquid and steam comparing each other. And then in conclusion, as the mass or change in temperature increases, the amount of heat transfer is also increased. The counter current flow arrangement seems to be more effective, though more trials would be desired to make a conclusive decision. And that's about it. Price?
Okay.